Hello everyone, today I want to share the art of compound interest. Compound interest is a key component to build wealth creation and also teaches the skill of honing patience. Like a blacksmith forging his metal into a sword, learning about compound interest will allow us to pave our financial path the way we want to. I view compound interest as an art as it can only be created with the skill of discipline. With that stated, let's deep dive into today's presentation about compound interest. The art of compound interest. Here are the table of contents. We're going to be taking a look at what interest is, the difference between simple and compound interest, give a definition of what snowball effect is, and give a real life example. Their names are Johnny and Jude. We're going to be visualizing compound interest and ending it off with the rule of 72. With that stated, let's get right to it. So, what is interest? Interest is the payment for the privilege of borrowing money. For example, it's the money the lender charges when you take out a loan to buy a home. This concept has been around the dawn of civilization, where mobility, trade, and commerce was flourishing. Interest rates provided capital for productive services, helping economic growth. Now that we know interest, let's compare the difference between simple and compound interest. Simple interest is the interest earned on the original principal only, whereas compound interest is the interest investors earn on the original investment plus all of the interest accumulated over time. Simply, it's just interest on top of interest. And I know I use the word interest a lot, but remember that simple interest is the interest on the principal amount only, whereas compound interest is interest on top of interest. Okay, and if that didn't make sense, don't worry, we have some examples to give. So, in this example, we have two characters, Bob and Joe. Bob decides to withdraw interest, whereas Joe reinvests his interest. So this is the main key differentiator. So let's take a look at Bob's case first. In the first year, Bob makes $1,000 in interest, which is calculated by getting our principal, $10,000, multiplied by the interest rate turned into a decimal, which is 0.1. So that's how we get 1,000. And by the end of year 3, Bob's total interest paid, 1,000 plus 1,000 plus 1,000 is $3,000. On the other hand, Joe reinvested his interest, increasing his interest paid every year. So in year 1, Joe makes the same as Bob, which is $1,000. The difference shows in year 2 as Joe doesn't withdraw but reinvests his earnings back into the principal. So our principal was $10,000, but with the reinvestment, it grew into $11,000. So the interest is paid on this new principal, which results in 11,000 times 0.1, which gives us 1,100. Joe repeats this process, and by the end of year 3, the total interest paid is $3,310. So over the course of 3 short years, Joe enjoys $310 gain in interest compared to Bob by contributing back to the principal and earning interest on a bigger share. To get a better understanding of compound interest, let's discuss the snowball effect, which is a perfect analogy of how compounding works. The snowball effect is the process of starting from an initial state of a small significance and builds upon itself, becoming larger and larger. So think about this snowball starting at the top of the mountain, and as the snowball rolls down, the ball will pick up more snow, gaining more mass and surface area, picking up even more snow and momentum as it's rolling along. As you reinvest your earnings, the principal amount invested grows, and when the interest rate applies to the new larger principal, the interest paid also grows. So over time, this small change leads to an exponential growth. And we're going to look at another example to show the snowball effect. I want to introduce you to Johnny, a single electrician living in California. We're going to take a deep dive into Johnny's finances to paint a real-life scenario. All of the numbers we're using for Johnny are based on the census data, Council for Community and Economic Research, U.S. Energy Administration, Bureau of Economic Analysis, and other data that aims to give an average cost. I rounded up the expenses and decreased the salary to give a conservative estimate. And make sure you guys know that everyone's circumstances are different, and I just wanted to highlight one possible scenario. Having kids increase costs, so by no means is this a one size fit all. This is just one example. Now, into the numbers. Johnny earns $36,000 yearly. That's his salary. But accounting for 20% in taxes, let's say that Johnny's take-home pay is $20,800. From the take-home pay, we need to account for expenditures to see how much Johnny is saving. So if we look at the categories over here, housing and utilities account for $9,542, healthcare, food and beverages, gas, and energy goods. I counted that as an essential expenditure, so this adds up to $21,498. And for personal expenditures, Johnny doesn't really spend as much, but on personal expenditures such as traveling, and he only spends around $2,302. And what he enjoys doing is going to movies and buying paint to color rocks. Johnny's a very creative person and loves to color rocks during his free time. It brings him joy. So this leaves us with $5,000 in savings, which is approximately 14% of his salary. He'll be using this money to feel the power of compound interest. So let's take a look what Johnny's going to be doing with this $5,000. Johnny will invest in the stock market as it has a higher yield compared to a savings account. The S&P 500, which stands for the Standard & Poor's 500 index, is an index of 500 publicly traded companies inside the US. Since its inception in 1957 to 2021, the annualized average return is around 10%, 10.5% to be precise. But we're going to go on the conservative side, and let's state that Johnny earned a 7% return. So, example time. Before we look at Johnny's returns, we need to introduce you to another character named Jude. Let's say that Jude is a mechanic and also has $5,000 to save. All right. I hope you guys can see my screen. Let's see if that's better. Okay, I'll leave this spreadsheet also in the description, so feel free to make a copy to meet your needs. On the left side, we have Jude using simple interest and Johnny on the right side using compound interest. The major difference between the two is that Jude withdraws the interest earned, whereas Johnny reinvests the earnings received. And if you guys don't know what earnings is, earnings here represents the capital gains and dividends. So if you follow the numbers and look at year 10, they both start at an initial $5,000, and how we got 350 is 5,000 times 0.07. And how I got 0.07 is the 7% returns. So if we follow down, Jude's principal does not increase, but Johnny reinvests the interest earned continuously into the principal, making it larger and larger and larger. And the interest also grows because our principal and interest is combined. I hope that makes sense. Looking at the numbers 10 years later, we can see that Johnny's initial $5,000 investment grew to $9,835, while the interest paid grew to nearly double to $688. On the other hand, Jude's initial $5,000 investment grew to $8,500, while the interest stayed stagnant at $350. Do you guys see the significance of compound interest over time? The small change of reinvesting grew the overall returns for Johnny. Johnny nearly doubled the interest paid from the beginning. And if we check back in 30 years later, Jude would have earned $10,500 in interest, and her initial $5,000 investment would have grown into $15,500. And that can be shown right here. $15,500. In contrast, Johnny would have earned $33,061 in interest, and the initial $5,000 investment would have grown to $38,061. Johnny earned more than double Jude's return on investment. And I also wanted to share this graph over here. If you guys didn't understand any of the numbers that I stated, my apologies. And hopefully this graph represents what I'm trying to say. So over here, this is Jude. This is the $5,000, the principal, which does not increase. Drew does not put in any money in. So this 5,000 stays the same for the 30 years. And then the total interest paid, it increases steadily. But this is also withdrawn. Johnny, on the other hand, his interest paid does not increase as much because it's reinvested. So if we look at Johnny's graph over here, look at the compounding that is occurring. And from 10 to 30, we could really see the drastic effect of the compounding interest. So by the end of year 30, $38,000. And I also wanted to show you, give you guys another example of what would happen if Johnny decides to contribute make a monthly contribution. So initial investment, Johnny will start at $5,000, and he saves $5,000 every single year, right? So how much does that mean that he could contribute in terms of month? So we have to do 5,000 divided by 12, which gives us $416. So $416, and let's give it a time of 30 years. And the interest rate, we're going to put at 7%, no variance in change, in range. And then this compound will happen annually, every single year. And if we calculate, look at that. The results are in 30 years, you will have $500,609.52. Not too shabby, right? For Johnny. This is incredible. Our single electrician, Johnny, is building generational wealth. Feel free to try this for yourself. I'll leave this link in the description below. Now, let's turn our focus back to the slides. I wanted to explain the math behind the formula. The compound interest formula is as follows. The total amount equals principal, which is the amount we're investing, multiplied by the interest rate divided by the number of times the interest is paid per year, raised to the number of times compounded times time. And we're going to give an example. Let's do this together. So the question states, an investment earns 3% compounded monthly. Find the value of an initial investment of $5,000 after 6 years. So what are we looking for? We're looking for A, which is the amount, right? And the givens is 3% compounded monthly. So if it's compounded monthly, our N is going to be 12. Monthly, how many months are in a year? 12, right? So that's how we get 12. And our 3%, it equals to 0.03 if we convert it to a decimal. And our P, which is our principal, our initial investment, is $5,000. And the T value is 6 years. So if you plug in all of those numbers into our formula, we get A equals $5,984.74. So this, after 6 years, our $5,000 initial investment would turn into nearly $6,000. Make sense? Okay. Since now we know the compound interest formula, this will be easy peasy. The rule of 72 is an approximation, and this is the formula. The years to double equals 72 divided by rate of return on investment, also known as the interest rate. And if you guys don't understand the numbers, the rule of 72 is just a way to calculate how long an investment will take to double given a fixed annual rate of interest. But there are some caveats to be aware of. First, for compounding interest, you get more precise result by using 69.3 instead of 72. We'll explain this in the next slide. The rule of 72 is an estimate, as 69.3 is hard for mental math. The number 72 divides easily by common rate of returns such as 2, 3, 4, 6, 8, 9, and 12. And secondly, the further you diverge from 8%, the less accurate your results will be. The optimal range of interest rate is 5 to 12, but always keep in mind that this is just an estimate. So, remember how we stated that we should use 69.3 for compound interest over the long term? We'll look at why now. The rule of 72 is almost identical to the compound interest formula, except the number of periods compounded is absent. Let's turn our focus to the example on the right. The question states, how many years does it take to double $10? On the left side of the equation, we have the future value, 20, which is double our principal amount, 10 on the right side. And inside the parentheses, we have 1 plus the interest rate represented as a decimal. Now this portion is raised to the number of years. And as we move to the second line, we divide the equation, the left and the right hand, by 10 to get the coefficients on one side. And then we take the natural log on both sides. The natural log property allows us to take the exponent to the front. So ln of 1 is 0, so we're left with natural log of 2 equal to the interest rate times t. The natural log of 2, if you plug it in the calculator, is approximately 0.693, and by isolating t by itself, we're able to calculate the year. All we have to do is plug in the interest rate and voila, you get the number of years it takes for $10 to double. And if you guys didn't follow any of the math that I just stated in this presentation, I just want you guys to know that the key takeaway, which is that compound interest requires time and creates wealth accumulation. And I like to finish off by sharing a quote from Albert Einstein. Compound interest is the 8th wonder of the world. He who understands it earns it. He who doesn't pays it. By Albert Einstein. Thank you guys so much for listening. I truly appreciate your time. And let's turn back to the face cam. Welcome back, everyone. Hope you guys enjoyed this presentation and learned a thing or two about the art of compound interest and the power it wields. I wanted to apologize in advance of my chippy-choppy lack of fluency in communicating these beautiful ideas, but I can assure you that over time I will improve. And thank you for your patience and your willingness to learn along with me. So, with that stated, feel free to check out the description and use the financial tools and resources to meet your needs. Alright. Thank you for your interest, and I'll talk to you guys really soon, alright? Take good care. Peace.